Hello everybody, my name is Jacob Hensley and today I will be presenting the final project for Introduction to Natural Language Processing. The goal of my project is to evaluate smaller LLM's performance on the task of code generation, i.e. natural language descriptions to Python functions. So given a short English problem statement from our database, the model must generate a Python function that passes the hidden unit tests. We evaluated multiple models such as 2 variants of DeepSeek, 2 variants of Quinn, and Llama. The main question for our project is which models work best for small programming problems and how does performance relate to model size? The motivation for this project is that small transformer-style models are increasingly being deployed on lower-end devices. For example, drones for military combat and surveillance, particularly in modern conflicts such as Ukraine. Farming equipment to allow farmers to monitor crop health, yield, detect pests, etc. IoT devices and other wearables are becoming more and more frequently integrated with AI. This project is useful because by comparing small model performance on a single benchmark, we get a more apples to apples fair comparison between their performance. And we are able to highlight the trade-off between model size, code specialization, and instruction tuning on task performance. For our evaluation data set, we chose MBPP, which is mostly basic Python problems. It's a collection of short Python programming problems, about 480 natural language to Python function training pairs. It also includes multiple hidden unit tests for each sample in the data set. Below you can see one example of a sample from our data set. You can see that the text is write a function to find the perimeter of a square. And the code, the gold standard code, I should say, is the function square perimeter, which returns 4 times the result, which we know is correct. The MBPP also includes multiple unit tests to go along with this function, as we can see that it asserts that 10 equals 40, 5 equals 20, and etc., etc. These tests will ensure that our model is actually generating correct and usable code and not just nonsense. Here is the prompt format we chose to go with for this project. We can see it starts with you are an expert Python programmer, task, and then it takes the task set and fills that in with the sample from the database. You must implement exactly this function signature. So in order to get the function signature, we actually run a regex function to extract just that one line from the gold standard code from the database so that we can put it here. The reason we need the model to use this exact function signature is because of the unit tests. The unit tests need this exact signature to run. Then we add a couple of requirements to nudge the model into the direction we want it to go, such as only outputting Python code, only one top-level function and not a lot of helper functions. No comments or explanations are necessary, and to not print anything unless otherwise stated by the problem. We tested a variety of models, each with their own characteristics and defining traits. DeepSeek Coder 1.3 billion instruction-tuned model is a small instruction-tuned code LLM optimized for code completion. Then DeepSeek 6.7 billion instruction is a larger model from the same family that provides better performance and better reasoning and will be a great comparison on showing how model size affects performance. Quinn 2.5 with 1.5 billion parameters and is instruction tuned is a code-focused model designed for natural language to code tasks, but it supports multiple languages, not just Python. Then we have Quinn 1.5, a previous version of Quinn from the same family, with 1.8 billion parameters, and this is a chat-tuned model. It's a general chat model with decent-ish coding ability, supposedly. We'll test that. Used as a dialogue baseline option for our one-shot coding generation. Then we have Meta's Llama with 1 billion parameters and is instruction-tuned. It's a compact general-purpose model as a small baseline against other code specialized models. So for our comparison, we'll be making two main evaluations. We will be comparing the code-focused models such as DeepSeek Coder and Quinn Coder that are heavily trained on source code and code-related instructions against more general-purpose chat-style models such as Quinn 1.5 and Llama 3.2. They're optimized for more broad natural language tasks, but can still generate code. This lets us see how much explicit code generation helps on the MPP-style programming problems compared to more general models. Then we want to compare model size versus performance. So we would like to see how scaling up the model affects its performance. So our model sizes range from approximately 1 billion parameters to 6.7 billion parameters, covering small, medium, and upper medium scale models. By keeping this task and decoding settings fixed, we observe how scaling parameter counts affect one-shot code generation quality, and hopefully we'll be able to see where diminishing returns start to kick in. For our experiment, every single model underwent the exact same evaluation pipeline to keep everything apples to apples. In this pipeline, for each of the 480 MBPP problems, we feed the natural language description as well as the gold standard function signature to the model. We then ask the model to generate 5 candidate solutions per problem, so every problem gets 5 different solutions. We then run this generated code against the provided unit tests to see which of these 5 pass, if any, and we then calculate the metrics and save the result to disk for further evaluation. So what are the metrics that we're going to be using? We will be using pass@5, which is the fraction of problems where at least one of the 5 solutions passed. So the other 4 could fail, and it doesn't matter. It will still count. Then we have pass@1, which is a fraction of problems where the first solution passed the evaluation. This is equivalent to saying it worked in the first attempt. And then code BLEU, which is a complex measure of similarity between generated code and reference solution. It uses more than just token similarity. It also uses syntax and code trees and a lot of complicated stuff to compare how similar two pieces of code really are. For model settings and hardware, our decoding strategy, for all models we used top K and top P sampling. We restrict to the first 50 most probable tokens to get rid of all the nonsensical tokens that are unlikely and will cause problems. Then we keep the smallest subset whose cumulative probability is at least 95% and sample from that test set. This matters because if we go too low, the model will output the same function for each of the 5 tests, and it will be boring, and it will get the same result. Too high, and it will output random and nonsensical code with low probability tokens. So this is an important parameter to tune. As for hardware, every single test was conducted on the iTiger HPC on a single NVIDIA RTX 5000 card with 16 gigabytes of RAM, and more particularly, we were on the iTiger 11 compute node. So here we can see the pass-K results for the models. So starting on the right, we can see that DeepSeek Coder 6.7 billion performed the best out of all the models, which is unsurprising given that it's multiple times more parameters. We can see that in the blue, which is pass 1, it achieved about a 45% chance of getting it in one go, which is great. And it received almost a 60% for pass 5, which means that out of all the problems, at least one of them passed 60% of the time. And then the per sample pass rate, which is just the average all samples, whether they passed or not, scored about 45 as well. We can see that Quinn 2.5 does not quite as well, about 10% worse in most categories. We can see that it got about almost 40% in pass 1 and sample generation, while it did pass 5 at almost 50%, which I think is pretty decent. One surprising result here is Quinn 1.5. Despite having 1.8 billion parameters, which is more than some of the others, given that it was not code specialized, it performed extremely poorly in all coding tasks, achieving only a 20% pass 5 rate, which is not very great. Then we have Meta's 3.2 Llama 3.2. It performed acceptably at about 40% pass 5 and almost, about 40% pass 5 and almost 30% pass 1 rates. But a model that performs slightly better is DeepSeek Coder with 1.3 billion parameters. It received almost a 50% pass rate in pass 5 and then about a 35% pass rate for pass 1, and then same for the per sample. So here we can see how going from DeepSeek Coder 1.3 billion to DeepSeek Coder 6.7 billion pretty drastically, by about 10% increased performance on the board right away. So model size clearly correlates to performance. Then we have the code BLEU results. Starting from the right, we have DeepSeek Coder 6.7 billion. We can see that it scored just over 35% in the overall, in the average overall best, which is the code blue from the best of the 5. And then in overall, it scored about 25%. And then you can also see in the light green and the light blue, we can see the average code blue per pass sample and the code blue per failed samples. We can see that Quinn performed slightly worse in these categories, which is representative of how it performed before. Quinn 1.5 performed slightly worse again, and then Llama performed even worse than Quinn on the code BLEU metrics in almost all categories. Then we have the DeepSeek 1.3 coder, which performed very similarly to its 6.7 counterpart. So what these results are showing us is that while code blue is probably better than BLEU as a metric for code quality, it is certainly not everything, and there seems to be very little correlation between these results and model performance. However, there is some. Here, these are the time in minutes that it took to run each of these tests. So keep in mind that we were running about 480 natural language pairs, and then we ran each one 5 times. So we can see that DeepSeek Coder 6.7 took the longest, given that it is the largest model. It took about 45 minutes. Quinn Coder took a great short time at around 21 minutes. Quinn 1.5, despite its quite terrible performance, was the second longest model to train, or not to train, to inference. Llama performed well and incredibly quickly. As we can see, it was the only one to even scratch the surface of the 10-minute barrier. And then DeepSeek 1.3 was about 30 minutes, which is about what we would expect. So what are the overall takeaways from this experiment? Well, as we expected, the overall best pick for code generation would be the largest model, DeepSeek Coder 6.7 billion. It had a very high pass rate at pass 5 at almost 60% and a per sample rate at almost 50%. This is a clear gain over the smaller model in its family, DeepSeek Coder 1.3 billion. It increased its model performance by over 10% at pass 1, showing that there are clear benefits of scaling within the same model family, at least at this size. Code specialization on small models. We compared the performance. Quinn 1.5 was slightly stronger on pass 1 than DeepSeek, but DeepSeek performed slightly better at pass 5. So these models are almost equivalent, but given their similar scale. Then we have the general instruction models. These were models that were not necessarily fine-tuned on code and are not necessarily code generation models. Llama was usable, but behind the other code models. Quinn 1.5 chat was clearly the weakest and performed poorly all over the board. The surprising results those results that surprised me are Llama performed much better than I expected, given that it was not a code specialized model and how long it took to inference. That will do it all. So thank you for listening. I appreciate it. I'll see you later. Thank you.